Welcome. So, we are looking into preconditioning techniques and we have discussed about left, right and split preconditioning, and this session we will look into how preconditioning techniques can be applied over conjugate gradient method or how conjugate gradient method can be modified if we are using a preconditioner. The first example of application of preconditioner we are considering to be conjugate gradient method, because conjugate gradient is only applicable for symmetric positive definite matrices, and therefore, we have to see that whether we can choose proper preconditioner so that symmetric positive definiteness is being maintained, and then how the resultant application comes out to be. Preconditioners can also be used over other solution techniques. However, because the fact that Krylov space based solvers are faster solvers, so we will only discussing preconditioner over Krylov subspace based solvers, because they are already faster solvers and we need to make them more fast. For steepest descent or for Gauss circle, we are not discussing preconditioning techniques, because instead of doing that, rather we will use Krylov space based solvers to get faster solutions. But when Krylov space based solvers are restricted due to the poor conditioning number of the matrix, we should think of using preconditioner so that we can get faster solution on top of that, so that we are not limited by the nature of the matrix. Well, so we will discuss two cases: left preconditioning, which is M inverse A x is equal to M inverse B, choosing symmetric positive definite M so that this matrix remains symmetric, so that this matrix M inverse A, this matrix remains symmetric positive definite, and conjugate gradient is only applicable when A is also a symmetric positive definite matrix. So, if M is symmetric positive definite, M inverse A will remain symmetric positive definite, and L inverse A transpose L inverse A L inverse transpose will also be a symmetric positive definite matrix. So, conjugate gradient will be applicable here. Both these equations can be solved using conjugate gradient. Now, we will see what is the implementation of that. So, original conjugate gradient method without any preconditioning, it starts with a guess x 0 and computes the initial residual r 0 is equal to x naught minus p and sets p naught is equal to r naught, and then obtain alpha and update x and r. Alpha is obtained using the A conjugacy of p vectors and orthogonalization of r vectors, which is r j transpose r j by a p j r j transpose a p j is alpha j. Similarly, we obtain another parameter beta j based on which p will be updated. So, obtain alpha and update x and r. So, once alpha is obtained, x and r is updated, and now use the updated r to obtain beta, and once beta is obtained, update the auxiliary vector p and then iterate for convergence. That means, do these steps again and again till you get a converged solution where the residual is a very small value. The mod of the L2 norm of this vector is a very small r, L2 norm of r is very small. So, now we will see how, if we consider a preconditioned system, how these equations will be modified. One idea can be that you explicitly compute an M inverse, multiply that with A, get M inverse A, multiply that with B, get M inverse B and solve it. But explicitly computing M inverse might be of problem at different stages, because we are thinking of inverting a matrix, or we are thinking of getting LU transformation of one particular matrix and then getting inversion and then doing a matrix multiplication. So, this might be of more complication. Rather, we will start with a matrix which has a form of M inverse A, and we will assume that through some method we are getting the M inverse A form. How we will discuss it later, and then we will apply conjugate gradient method over that M inverse A matrix. However, we will keep in mind that our original Krylov subspace is based on R 0 A, R 0 A square, R 0 etc. So, while calculating R, we use the property that R j plus 1 R j minus A alpha j A p j is orthogonal to R. So, left preconditioning of conjugate gradient will try to obtain steps for M inverse A x is equal to M inverse A with M being symmetric positive definite L L transpose. If M is L L transpose, M inverse A is also symmetric. Therefore, conjugate gradient can be obtained. We start with an initial guess x 0. Z 0 is the new residual which is M inverse B minus M inverse A x 0. Because the new equation system is M inverse A x minus M inverse B, the new residual is M inverse A x 0 subtracted from M inverse B, which is the new residual. The original residual equation has residual R naught is equal to B minus A x naught. The relation between the original residual and the new residual can be obtained as Z naught is equal to M inverse R naught. So, now if we are thinking of solving this equation, we have to go with the new residual which is Z naught, Z or Z naught. The precondition matrix equation is M inverse A x is equal to M inverse B. The residual of the above equation can be updated as very similarly M inverse A is the coefficient matrix now. So, if we can remember our older update was R j plus 1 is equal to alpha j is equal to R j plus 1 is equal to R j plus alpha j A p j. That is our older update for A x is equal to b equation. Now, we have an equation M inverse A x is equal to M inverse b and the residual is z, the residual is z. So, z can be updated very similarly as z j plus alpha j M inverse A p j. Now, R j and R was orthogonal as we are discussing M inverse when we are discussing A matrix. Now, when we will discuss M inverse A matrix, the new residual z j plus 1 and z j will be M orthogonal. That means, z j plus 1 z j transpose M z j plus 1 is equal to 0. So, dot product of z j with M z plus j plus 1 is equal to 0. That gives the parameter alpha as alpha j is z j transpose M z j divided by, if we substitute this here, if we substitute the z j plus 1 here, we get alpha j. So, we will substitute this as z j plus 1 and we will get an equation through which we can get alpha j is z j transpose M z j by M inverse A p j transpose M z j. So, this is M product dot product of z j transpose M z j, and this will be M dot product of M inverse A p j and z j. So, we will see how to simplify these products. Further, the auxiliary vector p can be updated. This auxiliary vector is now not auxiliary vector of x is equal to b, rather auxiliary vector of M inverse A x is equal to M inverse b. So, the update will have a relation with the new residual z. Earlier for x is equal to b. So, this is for M inverse x is equal to M inverse b, this is for this equation. For x is equal to b, the relation was something like R p j plus 1 is equal to R j plus 1 plus beta j p j. So, for the M inverse A x system, this will be p j plus 1 is equal to z j plus 1 plus beta j p j M inverse. This is the relation for x is equal to b conjugate gradient. Therefore, this should be similarly we can find out the relation for p update of the auxiliary vector in conjugate gradient applied over M inverse A x is equal to M inverse b or p j is equal to z j plus beta j p j minus 1. So, what we have already obtained a dot product between p j and z j, and now we will see how can we modify this. So, we got a relationship p j is equal to z j plus p j minus 1. So, this the given dot product which is M inverse A p j z j m is equal to M inverse A p j transpose m into z j, which will be the term z j will be p j minus beta p j minus 1. This is evident from here. So, when we will do this, we will have A p j transpose M inverse transpose, and M inverse transpose is same as M inverse, because M is a symmetric matrix. So, we will have minus and that other part will be beta j M inverse p j transpose M p j. Now, if we break it down, basically M inverse A p j M p j transpose M p j minus beta j, which is a constant and come out of it, scalar and come out of it, M inverse A p j transpose M inverse p j. And then we can write M inverse, say B M inverse B transpose is equal to B transpose M inverse transpose, and as M is a symmetric matrix. So, this will be B transpose M inverse. So, this will be A p j transpose M inverse M p j, M inverse M will be an identity matrix. Similarly, this is A p j transpose M inverse M p j, and p j and p j transpose A p j minus 1 will be a 0 vector, because P is an A conjugate matrix. P is A conjugate. So, we will see that this term will become 0. You can work it out, this is just one step, and this will be M inverse A p j transpose M p j, or M inverse A p j of M, as M is symmetric or M is LL transpose. Further, what we are discussing, M inverse A p j M is M inverse A p j transpose M j, which is M p j transpose, because we can change the order for in a dot product, M inverse p j transpose M inverse A p j, and as M transpose, M is symmetric. So, M transpose is equal to M. So, this will be an identity matrix, and we will get p j transpose A p j or A p j dot p j. So, the denominator of the alpha calculation is simplified to A p j transpose p j, and remember, this is the denominator what we obtained in conjugate gradient method also. However, the caveat is that the term p j is calculated differently in this method, because this is p j is an auxiliary vector of M inverse A x is equal to M inverse B, not for x is equal to B. Now, also z is equal to M inverse B minus M inverse x is equal to M inverse R. So, the M dot product of z j which is z j transpose M z j can be written as z j transpose R j or z j dot R j. So, my new alpha j, which was equal to, what was the initial form of alpha j? We will again just once check. The alpha j was z j m by M inverse A p j z j, and this is now transferred to z j dot R j, and this is transferred to p j dot A p j. This will be the new values, the final form of alpha, which the conjugate gradient solver algorithm will need to compute. So, the left precondition conjugate gradient steps will be start with x 0, which will give z 0 is equal to guess x naught, which will give the new residuals z naught is equal to m inverse a x naught minus m inverse b, set p naught is equal to z naught and r naught is equal to m inverse z naught. Obtain alpha and then update x and r and then z. So, if you can update r, you can update z or the same, and obtain beta using the updated r. So, the alpha is equal to r z z j by a p j r j, and you will obtain x j plus 1 is equal to x j plus alpha j p j. So, this also gives a direct way to update x instead of looking into z, because x is a solution vector, x is a solution vector. So, x will follow exactly same relation as it was following in the conjugate gradient method of x is equal to b. It will follow the same relation in the conjugate gradient method of m inverse x is equal to b, because x remains same in the both in both the cases. And r j plus 1. So, x j plus 1 is equal to x j plus alpha j p j. Similarly, r j can be obtained as r j minus alpha j a p j. Just substitute this into x is equal to b. X is equal to b equation is still holding, and z j plus 1 is m inverse r j plus 1. So, again it becomes important here to compute m inverse. M inverse should be readily available with us instead of actually looking into LU factorization of a matrix and getting the lower triangular form, multiplying it with upper triangular and inverse etcetera. M inverse should be readily available, that we need to check later. I will say that how m is evaluated, I will come into it later, which is also a very important part of these methods. But we will see that how the algorithms are modified provided we know to evaluate m and we are ready with m inverse or m inverse a in certain cases. So, once z is updated, you can update beta is z j plus 1 z j plus 1 z j plus 1's m dot product by z j m dot product. So, earlier they are beta was dot product of the vectors, now they are m products. And once beta is updated, update p as p is equal to r j plus 1 plus beta j p j, p z j, sorry, it is not r now, z p j plus 1 is z j plus 1 beta j p j. And then you can carry this p and r and z to get the new alpha, new beta, and continue on the iteration loop exactly the same way what you have done in conjugate gradient method, iterate for convergence. The conjugate gradients, we will probably once look into the methods. Okay. The conjugate gradient algorithm now can be formed using all these steps, starting with these gaps, start with this guess, use all these steps and then do the iterations, which is compute r 0 is equal to b minus a x 0, z 0 is m inverse r 0, p 0 is equal to z 0. For different iteration levels, first compute alpha r j dot z j by a p j dot p j. Now, in this calculation at least no m product is needed, m is not needed here, m is once needed at m inverse form here, but here m is not needed. Then x j plus 1 is equal to x j plus alpha j p j, r j plus 1 is equal to r j minus alpha j a p j, z j plus 1. So, this and this, if this holds, because this is the x vector remains essentially same, this should hold, then by b minus a x we can get this relation. This is okay. Once r is obtained, z is equal to m inverse r. So, we should know this, that r is equal to b minus a x, z is equal to m inverse b minus m inverse a x, which is the precondition systems, or m inverse r. So, then we get z is equal to m inverse r plus 1, beta is equal to r plus 1 z plus 1 by r j z j, which is earlier we have seen that beta is equal to z j plus 1 z j plus 1 m by z j m. Now, z transpose m transpose z sorry So, what is Z j plus 1, Z j plus 1 m, this will be Z j plus 1 transpose m Z j plus 1. I think we should some way redo it. We are trying to evaluate the beta, which will be equal to same. In a while we can check that Z j m, this product is equal to Z j transpose m Z j, and m z is equal to r. So, Z j transpose r or Z j r j, Z j dot r j. So, this will be Z j plus 1 dot r j plus 1 by Z j dot r j. This product will be this. So, we will get this particular beta evaluation from here. Z j plus 1 m Z j plus 1 will be nothing but dot product between Z j plus 1 and r j plus 1. And I will rewrite it for better clarity. And this will be Z j plus 1 dot r j plus 1, because Z j m product is Z j dot r and divided by Z j dot r j, which is calculated here, and we will get P j plus 1 is equal to Z j plus 1 plus beta j P j, the same way it should be right. So, we get a what we see that symmetricity of the matrix is preserved, that is how the M is chosen. So, that M inverse A is symmetric, and the solution is essentially very similar with the older conjugate gradient method. However, a new matrix inversion is added. This is a new matrix inversion which is added, that I have to calculate M inverse, and that is what we are telling, that M, this will be of further deliberation at the later stages, that how M inverse should be obtained, so that these steps do not add any extra overhead here. Well, we go to the split precondition conjugate gradient, which is L inverse A L inverse transpose u is equal to L inverse B, and this also needs solution of the equation that x is equal to L inverse transpose B. So, you get the following vectors and matrices: P hat is equal to L transpose P, u is equal to L transpose x, sorry, x is equal to L inverse transpose u. So, u, so that will give me u is equal to L transpose x, u is equal to L transpose x, r hat is equal to L transpose j z j, which is L inverse r j, because L this will see later, this comes from the previous discussion. So, r hat is equal to L j z j, z j is a new vector, and this is L inverse r j, and A hat is equal to L inverse A L inverse transpose, and the preconditioned equisystem is A tilde u is equal to L inverse B. So, this becomes this equation system, this becomes A hat. A hat u is equal to L inverse P. Now, conjugate gradient method similar to the left preconditioner conjugate gradient can be developed, and this method thus the following relationships can be utilized, which we have already seen with the older vector z j is equal to m inverse r j and p j is equal to z j plus 1 beta j p j by the new residual and auxiliary variables in the preconditioned systems. So, similarly, we will get r j dot z j is equal to r hat j dot r hat j and a p j dot p j is equal to a hat p hat j dot p hat j. So, the method this is the derivation of the method is very similar to the left preconditioned method. Only thing we have a new equation L inverse transpose, we are doing it in terms of u, a hat u is equal to L inverse transpose b and u is equal to L transpose u, the new equation system. So, we compute the initial residual r naught, get L inverse transpose r naught is r naught hat, obtain p naught is equal to L inverse transpose r naught, and instead of directly writing p naught is equal to z naught, this is the new form of p naught. Then we obtained alpha, we obtained update x, update r based on x update. So, you can write b minus x is equal to 0 and get r from x, and then update beta and get the p and do the iterations. The left precondition C G is supposed to solve A tilde u is equal to L inverse b and then find L transpose x is equal to u. However, in the present algorithm we are not explicitly evaluating u, rather it is modified to solve A x is equal to b. So, it is taken care of that both these sets of equations are solved together by the way we are defining r tilde and p and then using this p to evaluate update x, both these equation systems are taken care of. So, we are not solving it separately. However, something like L inverse transpose solution is required when we are finding out p, and L inverse A, this product is required when we are finding out r tilde. So, we are seeing that any of the preconditioned system is adding some sort of overhead in terms of solving a new equation system. So, this equation system, the L inverse transpose or L inverse A, these equation systems should be very we will have much should have much less complexity to solve. We should have some way readily available solution in n steps. We should not encounter n cube number of steps, some method in which we can get n steps. All variants of preconditioned C G preserve the symmetry of the preconditioned matrix. All variants give same iterates. So, we look into split preconditioning, we look into left preconditioning, even if we think of a right preconditioning, the iterate should be same, that is starting with the values x 0, the updated value of x at each iteration level must be same. Although it is claimed that condition number of the preconditioned matrix improve, the preconditioning increases new method introduces new equations like r tilde is equal to r tilde L inverse A p j or z is equal to m inverse r j. So, the inverses are less complex, this inverse is less complex if LU decomposition is of m is already available, then finding this inverse will be straightforward. So, next session, so we have to see that how LU inverse of m is available, but before doing that in the next session we will look into how preconditioning of GMRES is obtained. One group is for symmetric matrices, we have looked into conjugate gradient method. Now, for general matrices, non-symmetric matrices, we will look into the GMRES method and how preconditioned algorithm for GMRES is available, and then we will see, which is extremely important, that how the inverse of the M matrix or how the actual preconditioned matrix and its application over the solution vectors can be are obtained, so that the computational complexities due to the preconditioning itself is not high, that adds extra overhead on the solution methodology. So, we will also look into that in the next class. Thank you.